Good afternoon, everybody. This speech here is now about showing that a company like CABB, which is proud to be a purely chemical producing company, can still contribute to the megatrend of sustainability and green chemistry. Also why good old chemistry, organic chemistry, still qualifies and can be seen as chemistry in certain circumstances. We show how feedstock optimization and waste output can be optimized if you have the right technical fit to that and if you have the right processes and know how to do that. The presentation will run about the general introduction, the situation at CABB, to show you a little bit what CABB is all about, and then 4 or 5 case studies depending on the time, where I hope to be able to show you that green chemistry can very well be associated with the normal, regular, conventional chemistry. There had been a Roland Berger's study about how the chemical industry might look like in 2013. There have been identified main drivers and key drivers how the industry can be influenced and which megatrends the industry will be faced and need to attract and to focus on by 2013. There are these obvious points like the demand shift away from the Western to the Eastern markets, review of the competitive and environmental business models, commoditization of a lot of products which we have been producing as specialties over the years. Also the upcoming of biotechnology, needs for innovation, and also, and it's top on the list, is the need for sustainability. That is not only true now for the Western-based companies. I mean, we have been facing this already for years or for decades. It's also getting now a mega trend for Asian companies which have to look for better uses of resources. Already in the 1990s, the Green Chemical Institute, being part of the American Chemical Society, has been formulating principles and concepts which are still valid and which are still intact today. The obvious trends like atom economy, which calls for better use of feedstock, economical use of feedstocks, waste prevention, use of renewable feedstocks rather than synthetic feedstocks and raw material, safer chemicals, a safer way to handle chemistry, less hazardous chemistry, so more safety processing, designing of safer, leaner and less toxic chemical and processes, and chemical production strategy sometimes quite are in contrast to this, especially to this concepts for the sustainability. But the later example which I will show you will hopefully give an understanding that they are not contradictory in all and in every case to that. Some interesting statements from industry about especially hazardous chemistry. Obviously, hazardous chemistry is not able to serve very well the principle of green chemistry, as the synthetic routes are incorporating hazardous materials, toxic materials itself. Also, however, need to be considered that if these risks and if these toxic and hazardous things can be contained and can be mastered, then going through a hazardous chemistry, which normally means a more reactive chemistry, might be the better and even the safer way than going the longer alternative pathway. In this context, it's interesting to note that chlorine, which is certainly associated always as not being a green chemical and being a very hazardous material, is still one of the most important chemicals in the chemical industry and in the reductions, and in the reactions, sorry. It is very unlikely that chlorine, chlorides, and intermediates containing chlorines can be substituted in total. The chemical production contains more than 50% of the products containing chlorines, and even in pharmaceutical, which are assumed to be very consumer friendly and very safe, around 85% of the products containing chlorides or have been seen chlorine through the synthesis. These are older figures, some 6 or 7 years dated out, but they're still having valid today. Study showed that sustainability and optimizing of chemical processes is very important to fine chemical and pharma companies. Normally, for measuring these kind of influences and measuring optimization in this sustainability and green chemistry approach, it has been agreed to concentrate on two factors in metrics. One is the PMI, the process mass intensity, which is defined as part of the input materials being part of the products which you get out of that. So purely focusing on everything which you put into the synthesis in comparison to what you get out of it. While the so-called E factor is concentrating on the waste as a part of the production volume which you get out of that. Unfortunately, none of these factors and none of these metrics taking into consumpting the energy spent. We all know that this is getting a more critical one. This is also environmental dictating, and we have been taking out that in the sample separately and considering that in the sample which will follow separately. Interesting to see that companies, pharma companies, are triggering to substitute certain very well-known and well-contributing chemical reactions which have been around for decades and centuries, like bromination, reduction, sulfonation, chlorosulfonations, amide formation, Friedel Crafts, all of this been associated with very hazardous input material reagents and with low waste growth. Amide bond formation, for instance, I mean, it's still in a study of 128 selected drug products, around 65% of the synthesis were still using amide function. So that is still an important tool. And more than 40% out of the 65% of amide bond formations are done via chlorides, giving rise to HCl and SO2 acids off gases. Coming to CABB sustainability at CABB. In generally, we are a vertical integrated and global acting company producing fine chemicals up to custom manufacturing solutions. We are a medium-sized company focusing on mainly building blocks, also some active, based on various distinct technologies about chlorination and sulfonation mainly. We're a global leader in monochromatic acid, certainly not a compound which is associated to be green. We are a young company, but we are a company which has centuries of history, in most cases more than 80 decades of histories of the single companies. That's around 1,000 employees, 400 million euro of sales, with production sites in Germany, Finland, Switzerland, and in India. The backbone and the big contributor to our sustainability concept is a back integration and a recycling infrastructure which we do operate. The basic raw material which we are using, as you see, is sulfur, liquid sulfur, and the other side it is salt. We are operating a chlorine electrolyzer, which is only for our internal chlorine consume, as we are operating a sulfuric acid plant. The basic raw material out of that, the chlorine sulfur trioxide, are used to make the chlorination, sulfonation products, and these are used to produce our catalog products, intermediates, up to the advanced intermediates. We are processing alone every year 10,000 of tons thionyl chloride, giving rise to approximately 15,000 tons of SO2 and 20,000 tons of H2L off gas. We have a concept on place at one site where we separate these off gas stream completely, separating them, cleaning them up, and feeding them back to the process. The SO2 is going back to the sulfuric acid plant to produce sulfur trioxide, which is then used again internally to produce all these sulfonation products. The HCl is mainly transformed into hydrochloric acid, which we sell on the market. Sustainability to CABB or in CABB means combining economical advantages with environmental friendly and social responsibility. We are 10 kilometers out of the third largest city in Switzerland, so we need to know what we do there. The Verbund system is saving resources, energy, and minimizing emission and logistical and infrastructures costs. It's added value through the whole value chain up to active ingredients, and we can recycle output out of our products, co-products or waste into sales products. Needless to say that with having this kind of chemistry in place, we have a knowledge and a know-how of decades of run this kind of chemistry safely. Now let's come to the first example. The first example is about an intermediate for an agro product. It's produced on 100 tons level per year. It gives a good example of optimization and sustainability with regards to change from a batch process to the continuous process. It's a methylation reaction which originally was run and was transferred to us as a batch process. Over the years, we have completely turned that into a continuous production process, utilizing still the same batch equipment. This is the process how it came to us. It is utilizing 2 reactors. We have consecutively feed of reagents and of raw materials in the different reactors. It's an extremely energy consuming process because we have heating and cooling cycles. Also, you have to heat up in the reaction for the first reactor, then you have to cool it down before transferring it to the second reactor. You heat it up again, you cool it down. The new process now utilizes only one of the reactors. It's a parallel dosing of reactants and of raw materials. And we have a continuous overflow of the reaction mass, which then is continuously worked up in a separate stream. I mean, obviously, the heating and the cooling cycles are decreased to a minimum what is required, which has a tremendous effect on the PME and on the E factor. You see down in the green boxes the E factors and the PMI. The blue boxes give you an overview about the save of electricity. The example quite well shows what's turning a batch process into a continuous process with all the advantage which you have. You have a larger output per day because you don't have the heating and the cooling. The energy saving of that has a tremendous effect on using less raw material, creating less waste, and saving a lot of energy in this process. Next process is quite typical for what we are doing at CABB. It's a chlorination of an alcohol or an acid with thionyl chloride, giving rise to HCl and SO2 acidic off gases. We want to show in this example only the effect of the Verbund system versus the regular system, what you would do, the HCl and SOS collected in scrubber and wash it down with caustic to create wastewater. So for doing that, we have assumed that also our internal process is a batch process to simplify and to line it and to have a like-to-like comparison to the normal batch process. Generally, and in reality, we are running all of this chlorination in a continuous, but in that we have only now considered that as batch so that we can compare better the Verbund system influence on the HCl and SO2 workup. So a regular or conventional process would do the chlorination with the carburic acid, and let's assume it's without an organic solvent, which is very often the case. The SO2 and HCl is going to a scrubber, is washed down with caustic, resulting in a huge waste load with big salt load, which you would need to get rid of. And opposite to all the chlorination within CABB, and again, could remind you that we are processing several 10,000 tons of thionyl chloride for chlorination every year. It has, of course, the same matrix during the reaction. The SO2 and HCl, however, is collected in a separated plant. It's cleaned up, it's separated. The HCl is confirmed to hydrochloric acid, which is a sales product and completely goes into sales, while the SO2 is recycled via our sulfuric acid plants, and finally via the sulfur trioxide out of that can be reused for thionyl chloride, which is fed again into the chlorination process. Also here, of course, the impact is enormous, which you have if you use a system which can cope with waste or with off gases out of your process. Another point is that in conventional process you would buy in thionyl chloride, so you would essentially buy in sulfur and you would buy in chlorine. If you run all these off gases to a scrubber, then you will lose the whole sulfur out of your thionyl chloride which you paid for. You also use one of the chlorine which you paid for. So even, especially in times where sulfur prices and chlorine prices are hiking, and that's a very costly alternative. With us, 100% of the sulfur and 100% of the not used chlorine is completely recycled, and at the end of the day, going back into the cycles again. This is a very typical example It's an intermediate for a blockbuster, which is produced on ton levels at CABB. It's quite typical in the phase that it's a sulfonation, then a chlorosulfonation, followed by an amidation, which is typically done in 2 to 3 steps using 1 or 2 different solvents. In this case, this is the literature study. It's 2 solvents which you need to change. And normally you also have at least 1 isolation within within the synthesis. What we did at CABB, we turned it around into a 1-pot synthesis. It's a 1-pot synthesis with not utilizing any organic solvent. All of the organic solvent, there were 2 in the old process, are dissolved by alternative kind of solvents. So we're using SO2 as the solvent in the first sulfonation step. The SO2 then is completely recycled again back to our Verbund system, and we're using the second step, the sulfonyl chloride, the chlorination reactant, as a solvent ourselves. The chlorosulfonic acid is substituted by sulfur trioxide, an equimolar amount of sulfur trioxide plus the thionyl chloride chlorination after that. So the waste which is you're getting out of the original on the conventional chlorosulfonic acid chlorination, the sulfuric acid is also prevented. PMI factors, and especially the E factor, who is a measure for the waste load which you create through a synthesis, are dramatically down. And again, I mean, this is mainly due to the complete substituting of organic solvents and to the prevention of sulfuric acid waste out of the chlorosulfonic acid use. A very interesting example in the case of green chemistry, and this is mainly referring to the mandate of green chemistry: run safer chemistry, make processes much safer, is this special Wolff-Kirchner reduction. It's a very critical Wolff-Kirchner reaction involving hydrazine as a reagent, as a key reagent. It's an extremely exothermic reaction, and it's a very critical to control and very critical to run. This process has been run by a competitor in Asia, and he has not been able to get this under control in a batch reaction. The yields were low, the quality was not represented from batch to batch, and even more, there were incidents associated with that before he stopped producing that. We had been picking up this process. I cannot provide you with comparison because this process is simply not possible to scale up on a batch as a batch process. So the problem is the spontaneous involvement of nitrogen at a certain point in this reaction. And this is created in a very narrow range of temperature. So it is up to 150 degrees, no evaluation of nitrogen, but then you step up between 2 and 5, there is a spontaneous involvement of all the nitrogen. So very critical to control reaction mixture. What we finally did is redesign this to safe continuous process. We have been patterning this process even because there was so much work into going into that. It's so much of an advantage along the conventional process. It gives a good example how a process can be turned into a safe process by changing it with know-how which you have and which CABB especially have, with the case of know-how handling this kind of material, this hazardous material, and with reshaping batch processes to kind of continuous processes. Normally, looking at this in an academic way, this is exactly this kind of chemistry, exothermic, extremely exothermic, which was called for downsizing, going to microreactors. We were able to keep our general equipment. We are running this on a multiple ton basis to keep our general fine chemical assets and turn the synthesis around so that we can still utilize that rather than going to microreactor stuff where we don't have expertise. Last process and last example is about, again, an amide, an intermediate for pharma for an early development, and to show the effect which you have, and you can exchange a solvent again via a non-organic solvent. The process is normally run in THF. We have been able to turn that around in using water. There had been considerably lower costs to that because THF is an extremely expensive raw material, organic solvent. We even got benefited in addition on that, as we could run the reaction in more concentration, higher concentration, and get more output from the same reactor volume. Also here you see tremendous effects, which come from just getting rid of an organic solvent. I mean, we were very lucky that we could start that in water, because that is, of course, is much more easier to dispose. You can see the factor especially in the E factor. Again, the E factor is a factor for the measure of waste per kilograms of product. And you also have tremendous effects on the energy savings, which comes from that you don't have to change in the synthesis from one organic solvent to another organic solvent by distilling off, cooling again, heating up again. All right, I hope I was able to show you a little bit that conventional chemistry still qualifies in the area of green chemistry. To summarize, CABB performs chlorination, sulfonation, chlorosulfonation, all kind of this hazardous and nasty chemistry in a highly efficient way, taking advantage of the Verbund system at one of our sites. We can carry out hazardous chemistry in a safe, in a contaminant way, in closed system, highly sophisticated processes and equipment. We have long history of doing that, and I will find it again. We are 10 kilometers out of Basel. I mean, we are in a housing area, and we know how to handle this chemistry safely. CABB combines the advantages of its Verbund and recycling system with multi-purpose fine chemical assets and production, and so that these can benefit from them. Thanks a lot for listening, and if there are any questions, I would be happy to answer.